Okay, so now we're going to finish the proof of the wedge product formula. So the first thing, in the end of the last video, I had the wrong thing here. So this isn't x sub sigma of m, it's x sub p sub sigma of m. Remember how we define this notation here. Okay, so we want to show that the left-hand side is equal to the right-hand side. So it's going to be a little bit complicated. So we aren't going to be able to show that every term on the left is equal to some term on the right. And that's actually not what we want, because we have this sort of k factorial L factorial division thing, which is telling us that we've done some kind of weird overcount. But I'll show you sort of, I'll give you an example of how we're gonna convince ourselves both sides are equal, and then explain the general argument. So let's think about how we're going to account for, let's do the example of R3, and then how to account for example, sigma equals the permutation 3, 1, 2. So what does this mean? This is the term. Okay, so here I'm switching 1 and 2. Actually, what is the sign of this? So 1, 2, 3. I can switch to 1 and 2, 2, 1, 3. I'll switch the 1 and 3. Actually, no, you know what? I'll switch the 2 and 3. So it's 1, 3, 2. And then I'll switch the 3 and the 1, 3, 1, 2. So the sign is just 1. And what I'll end up getting then is the term product from m equals 1 to, okay, so, and let's use k equals 2, L equals 1. And let's have I be just 1, 2, and j be 3 for simplicity. So then sigma is 3, 1, 2. So what I end up getting in my product is dx1 applied to, sorry, dx3 applied to v1, dx1 applied to v2, and dx3, 2 applied to v1. And let's, instead of using x1, x2, x3, let's just use normal x, y, z coordinates in this setting here. Okay, so how am I going to account for this term on the right-hand side? So the first thing I'm going to use is set tau equal to sigma inverse, which is, in this case, that's 2, 3, 1. So why am I doing this? Well, notice that in the upper equation, I have this property that when I take sigma of the subscript of the vector, I get the subscript of p of the coordinate. So what I want here, now my permutation is happening in the vector, but what I want is, I want sigma of tau of 1 to equal 1. And I would want sigma of tau of k to equal k, etc. And that will give me, at least along the diagonal, that will give me exactly the elements here. So if I set these equal to each other, then I get on the right-hand side the determinant dx applied to v1, dy applied to v1, dx applied to v2, dy applied to v2, and then I have to multiply it by the same term for, oh, sorry, not, these are all wrong, right? These are, these. So I'll get dx applied to, these subscripts are all wrong. So I'll get dx applied to the tau of 1, which is 2. And then tau of 2, which is 3. And then tau of 3, which is 1. Okay, then now this equals dx of v2, dy of v3, dz of v1, minus dx of v3, dy of v2, dz of v1. Okay, so we're looking really good because we almost have equality. So I have this term, and it's equal to this term. But I have this pesky other term that I have to deal with, right? Where I've plugged in, where I've swapped what I've plugged into x and to y. Oh, wait. This should be 3 here. No. That should be a 1. This one should be a 3, sorry. 1, 2, 3. Right, and that's exactly what I have. So these are the two circle terms are the same. So what am I going to do to deal with this other term? Well, let's set tau equal to sort of 2, 1, 3, but with the first two terms switched. So 3, 2, 1, which is equal to 2, 3, 1. Sorry, not 2, 1, 3, 2, 3, 1, but I've switched the first two terms. So it's a permutation that leaves this last piece fixed, but switches something in the first part. So then what I get on the right-hand side, I get a minus sign because the sign of tau is now 1 off from the sign of sigma inverse. And I'll get same thing dz of v1, but now dx dy. Now I need to be plugging in v3 first, and then v2. And then this is going to give me minus dx of v3 times dy of v2, dz of v1 plus dx of v2, dy of v3, dz of v1. And now, if I add these two things together, which I am doing because I'm taking the sum, right, over all such taus, then I'm going to get that the terms from sorry, I should do these all in the same color. These pink terms are all the same, and I now have these terms, which I'll outline. Actually, green doesn't look too good. I'll outline them in purple, and they have a negative sign. Okay, so that almost works, right? Because in this case, k is equal to 2. So 1 over k factorial L factorial is equal to 1/2. So I've gotten my 3, 1, 2 term accounted for by setting tau equal to 2, 3, 1, and then tau equal to 3, 3, 2, 1. But now I have these purple terms with a minus sign. But the great thing about the purple terms is the purple terms correspond to sigma equaling the inverse of either 3, sigma equaling, the inverse of 3, 2, 1, inverse. So, right, because, everything on the right-hand side also has to be accounted for on the left-hand side. So, and 3, 2, 1 inverse, well, it's whatever I set to get 3, 2, and 1, which is 3, 2, and 1, it's actually its own inverse. So, so then when I actually do the sum over all sigma on the left-hand side, I'll have a 3, 1, 2, and that'll be accounted for. So the sum of sigma equaling 3, 1, 2 and 3, 2, 1 is accounted for by the sum of tau equaling sigma inverse, and then so 3, 1, 2 inverse, and then 3, 2, 1 inverse. So i.e. the sum of the terms on the left-hand side with sigma equals 3, 1, 2 and 3, 2, 1 is equal to the sum on the right-hand side with tau equaling 3, 1, 2 inverse and 3, 2, 1 inverse, which is 3, 2, 1, and then 3, 1, 2 inverse is 2, 3, 1. Okay, and everything is accounted for because in basically what's happening is that on this side, every time I see one of these terms, when I set tau to be the appropriate thing, I get that term. When I set tau to be sigma inverse, I get that term along the diagonal. And I also get all these extra terms. And all those extra terms are accounted for by the k factorial L factorial. So what's actually happening is when I'm proving the actual theorem, not just in the special case, is to account for sigma, set tau equal to sigma inverse. But this will now add with some signs that we're not going to actually discuss. Then on the right-hand side, you'll get sort of the sigma term plus some other terms. But they differ by a permutation which keeps the first, which is like only within the first k and then the last L. So which never mixes the first k and the last L. So for example, this permutation, sending the first to the second, it doesn't mix in with the last number. And so then adding over all perms tau on the right-hand side of the form sigma inverse composed with a permutation which only move the first k or the last L gives, so if you add over all of them, you get k factorial L factorial times sigma's contribution. It should be, let me see. Yeah, it should be sigma k factorial L factorial times sigma's contribution plus the contribution from, well, plus k factorial L factorial times the contribution from the inverses of sort of all of these other taus you obtained in this way. So the idea is that why is it k factorial L factorial? Because there's k factorial permutations that just move the first k, L factorial that just move the first L, and then you multiply them to get all of them that don't mix. And so basically, it's just the proof in general is just a souped up version of what we did here in the k equals 2, L equals 1 case, where I is 1, 2, and j equals 3. You just fix I and j. So basically I think to understand what's going on, the best way to do it is to just do some more simple examples like this, and you'll see exactly what's popping up. So when you fix sigma, pick tau inverse, you'll get some like term that where the sigma term on the left and this tau term on the right don't match, then set tau to be sort of this second term given by the second term, and sigma prime, like another sigma, to be the inverse of this new tau, and you'll get exactly that the sum of the terms with these sigmas is equal to the sum on the right-hand side divided by k factorial L factorial.